All right, welcome everyone. Today we're going to continue talking about power series representations. And in the examples we're going to look at, we're going to see kind of the hands-on approach for how we actually integrate a power series. So we looked at technically how we do it last time with our main theorem, and we looked at a few examples where, with differentiation, how we differentiate a power series. And integration is going to be very similar. So for derivatives, we differentiate term by term, and integration is going to be very similar. We integrate term by term. So let's look at example 3. We're going to find a power series representation for this function natural log 2 plus x. And to get us started, let's write down, we have our kind of our prototype that we're trying to always refer back to. This is the one series that we're always trying to look to see if this is similar. And this is for the function 1 over 1 minus x. And we know we can write that as the sum from n equals 0 to infinity of x to the power n. And this works when the absolute value of x is less than 1. All right, so that's the series we're always trying to refer back to. Now, this function, natural log 2 plus x, is not in that form. It's not 1 over 1 minus x. It's not a fraction yet. But we have some calculus we can use. We could either try to integrate this thing, or we could try to differentiate to see maybe we do get, maybe its derivative is similar to this form, or maybe its integral is similar. And it turns out you could try either one. You could try integrating, you could try differentiating. But it turns out differentiation, if we were to differentiate this function, natural log 2 plus x, if we were to do the derivative of this, what would be the derivative? Well, it'd be 1 over 2 plus x times the derivative of 2 plus x. And derivative of 2 plus x is just 1. So the derivative of natural log 2 plus x, doing a little chain rule here, derivative of natural log 2 plus x is 1 over 2 plus x. So that's pretty close to our kind of this format that we're always trying to refer back to for these power series representations, 1 over 1 minus x. Now there's a few adjustments we need to make here. So for instance, this 2 doesn't match up with the 1. And we have an addition sign here that doesn't match up with the subtraction, but we've seen how to handle these before. So we can do a few things. To deal with this 2, let's kind of get this into the correct format. So let's reformat this function a little bit with just some algebra. So we could write that as 1 over 2 plus 2x over 2. Now why we're doing this is so we can factor out a 2. So if we factor out a 2 from the denominator there's a 2 here, there's a 2 here, factor that out, and we're going to break that into its own separate fraction. So we're going to break that into a 1/2 times 1 over 1 plus x over 2. And that gets us the 1. Now we need to make that addition sign. We need to have subtraction, so that's where we're going to introduce our double negative. So we'll have 1 minus negative x over 2. And what we'll do is we've been working with this 1 over 2 plus x. We have it now in the correct format where we can just apply this standard formula that we're using. And we're just going to find the power series representation. Well, we're really going to focus in on this term here. And that's what we're going to do. We're going to do the power series representation for our derivative. So we are going to have a 1/2 in front. And then what's the representation for this fraction? Well, the ratio here, the common ratio, is this negative x over 2. That's our variable part. So what we're going to do is we're going to plug that in to our formula. So negative x over 2, we're going to be placing that into this formula for wherever we see an x. And that tells us then we're going to have the sum from n equals 0 to infinity of negative x over 2 raised to the power n. So I've just replaced this x that we see here with what we have in our a reformatted version of our function, this negative x over 2. So like the variable part here is negative x over 2. That's kind of the common ratio, the r value for our geometric series that we're kind of plugging in here. All right. So let's simplify this down a little bit. We can do that. So let's split up this is pretty nice actually, but let's split this up. So that negative x raised to the power n over 2, we can rewrite that as the sum from n equals 0 to infinity. Let's write it as negative 1 raised to the power n. And then in the denominator, we'll have 2 raised to the power n. And then we'll have our x times x raised to the power n. We've just kind of separated all of those. And a lot of time that's helpful because we know that negative 1 to the power n, it's helpful to really kind of reproduce that because we know it's an alternating series then. We can do one more thing. We have this 1/2 in front. Let's bring the 1/2 inside, and it'll become 2 to the n plus 1 then when we do that. So we're going to have the sum from n equals 0 to infinity of negative 1 raised to the power n over 2 to the n plus 1 times x to the n. So we've just brought this constant multiple in front. We've brought it inside the power series here. We can do that because there's no n attached. And then we just add 1 to the exponent. So we go from 2 to the n up to 2 to the n plus 1. All right, so here's a power series representation for 1 over 2 plus x. So it's not the power series for the function that we're actually interested in. And so what we need to do is we started with natural log, we differentiated, that gave us 1 over 2 plus x. We found the power series representation for that function, so to work backwards, we have to undo the derivative. And how do we undo the derivative? With integration. So we have to integrate this power series. So we want to integrate this power series. And what does the integration look like? Well, we're going to, remember, we're integrating. X is our variable. So this is just a power. Essentially, we're just going to be integrating power functions. So we're just going to be doing power rule a whole bunch of times. And we're going term by term. So we really just focus in on integrating everything, our general term. We're going to integrate this general term, keeping in mind that x is our variable. So if we're looking inside the summation here, we're thinking of n as just a fixed number. You know, we're adding it in. It's our index. X is our variable. So x to the n is what we're going to integrate. So when we do this, we're going to have the sum. Let's leave a little bit of room there. We're going to have the sum from n equals 0 to infinity. So that negative 1 to the n and 2 to the n plus 1, those are just constant multiples. So those nothing's going to happen to those. So they're going to stay the same, negative 1 to the n over 2 to the n plus 1. And let's do the power rule on that x to the n. So what do? Keep our variable the same, add 1 to the exponent. So we go from n up to n plus 1, take that new exponent, flip it, put it in front. So 1 over n plus 1. And so there's our power series representation for natural log 2 plus x, with one slight exception. We're not done yet. So what do we do whenever we integrate? So here we're integrating a function. Slightly different format than what we're normally used to, but this is a perfectly good function. We're integrating it. And what do we normally include when we integrate? Find the antiderivative. Well, a plus c. So the next step of this is to actually find a value for plus c. So if we were just interested in finding the antiderivative, then we just generally include plus c, and that's the end of it. But here we're trying to find the exact representation for natural log 2 plus x. So we have a specific function in mind that we want this power series to represent. So plus c can't be just some arbitrary constant. We have to figure out what value for c will make this power series representation match up perfectly with this function. All right. So let's see how to do this. This will be the next step. All right, so what have we found so far? We found that the natural log of 2 plus x is equal to constant c plus the sum from n equals 0 to infinity of negative 1 raised to the power n over 2 raised to the n plus 1 times 1 over n plus 1 times x to the power n plus 1. So there was our power series, or our power rule there. And to find c, what we're going to do is we're going to plug in an x value. And so what x value could we plug in, keeping in mind that a lot of the terms here are just x raised to the power n plus 1, so a lot of these are just powers of x. A good one to plug in is x equal to 0. So that's what we're going to do. We're going to plug x equal to 0 into this power series. And let's just, to really emphasize this, let's write out the first few terms just to see what's going to happen, just to help us. So we have c, and then what happens when n is 0? What is the first term there? Well, we're going to have 1/2 times x. And then so this is our n equals 0 term. What about n equals 1? Well, there we'll have minus, so it's going to be negative. And then when n is 1, we're going to have 1/4 times 1/2 x squared. And maybe one more. What about n equals 2? So when n is 2, we're going to have, this is going to be positive 1. And then we'll have 2 to the power 3. So plus 1 over 8. And then 1 over times 1 over 3 x cubed. And so on. All right, so we've written out the first few terms of our power series, and we have this value for this plus c term in front. What we're going to do is we're going to plug x equals 0 into this equation. So let's see what we get. Plug it into both sides. So on the left-hand side, we're going to get natural log of 2 plus 0 is equal to c plus the sum from n equals 0 to infinity of negative 1 raised to the power n over 2n plus 1 times 1 over n plus 1 times 0 raised to the n plus 1. And if we look at all of these, the first few terms here, they're all powers of x. So essentially we're plugging x in here, or x equals 0 into here, x equals 0 into here, x equals 0 into here, and so on. And each of these is just going to be 0. They're just powers of 0. So it's helpful to write out the first few terms here just to see. Sometimes with your starting index, you might have the first number, maybe the first couple numbers. It depends on the series. But probably the first number, you might actually have a constant. So you do want to just check that. But here it turns out that all of these terms here, when we plug 0 in, are just going to give us 0. So all terms are going to give us Again, that's not always the case. So there are power series out there where you might start with just a constant here that doesn't have an x. So when you plug x equals 0 in, that will still have a contribution. But for this specific example, every single term of our power series here has an x in it. So when we plug x equals 0 in, it's just going to become 0. So really, all of this is just 0. So what we're left with then is the equation natural log of 2 is equal to c. And there we go. We found our c value. So we can say the natural log of 2 plus x is equal to the natural log of 2 plus the sum from n equals 0 to infinity of -1 raised to the power n over 2 raised to the power n plus 1 times 1 over n plus 1, x raised to the n plus 1. So we've just essentially filled in this value for c. We've filled it in. And there we go. We have a nice power series representation for this natural log function. And really what allowed us to get this, if we go back, we started with our function. It wasn't in the correct format here for that 1 over 1 minus x form, but doing the derivative brought us something very close. We had to do a little bit of reformatting, but once we were there, we were able to find our power series representation for the derivative, which is all well and good, but it's not the power series for our actual function. We had to kind of integrate back. So we did the derivative, found the power series, and then to undo that derivative, we integrate. Now the issue with derivatives is you lose a little bit of information. Every time you differentiate, you lose a little bit of information. So integration doesn't perfectly recover the original function, and that's what this plus c is. There's a slightly unknown bit of information here that we have to kind of figure out. So integrating gave us our power series almost, except that plus c. And then the last part of that was actually figuring out what plus c was. And then we were able to write down our nice power series here. All right, so let's find the radius of convergence. And we know when we differentiate and when we integrate, the radius of convergence stays the same. So let's look at this power series that we started with. We started with this sum from n equals 0 to infinity of -x over 2 raised to the n. Let's figure out what the radius of convergence is for that. And then the radius of convergence for the one we're actually interested in is going to be the same. All right, so let's start with our original power series. So this was 1/2 times the sum from n equals 0 to infinity of -x over 2 raised to the power n. And this is a geometric series, and we know a geometric series converges when this variable part, this ratio here, the r value, when the absolute value of it is less than 1. So let's simplify this inequality. So it converges. The absolute value cancels off the negative. 2 is a positive, so we can write this as the absolute value of x over 2 is less than 1. Multiply both sides by 2. That gives us the absolute value of x is less than 2. And once we have our x term by itself, the number on the other side, that's our radius of convergence. We could also write this as an interval. So this would be the x values where x is greater than -2 but less than +2. Or the open interval from -2 to 2. And you can, if we're thinking radius of convergence, it's half the width. The width of this interval is 4, so half of the width would be 2. So, there's a few options here for how you want to think of the radius. Pick the one you like the best. So our radius of convergence for that original series is r equal to 2. So again, you can think of that as this number here, or once you have x by itself, or it's just half of the width. So the interval here has a width of 4, so the radius is half that. All right, so our original power series had a radius of convergence 2. That means once we integrate this, we're still going to have the same radius of convergence. So our power series for ln 2 plus x, and what was that? Test my memory here. Natural log 2 plus the sum from n equals 0 to infinity of -1 raised to the n over 2 to the n plus 1 times 1 over n plus 1 times x raised to the n plus 1. I think I got it. This power series has to have the same radius of convergence. So r equals 2. All right. So there we go. Our original power series was a nice geometric form, so we were able to find the radius of convergence by this little inequality argument. And then our power series for natural log 2 plus x, even though it's a much more complicated series, has to have the same radius of convergence. All right. And that's because integration and differentiation, they don't change the interval or the radius of convergence. Let's try one more example here, just to get a little bit more practice with integrating a power series. So let's look at example 4. We're going to see how to use this with definite integrals. And this is one of those places where power series, you're going to see them actually be quite useful. We're going to have integrals like this, which are pretty difficult to do, to find a nice kind of closed form antiderivative. But for power series, the integration part is not going to be that bad. All right, so we want to do this definite integral, and we're going to use a power series to help us do it. So this is the integral from 0 to 1/2 of x over 1 plus x to the power 5. We're integrating with respect to x. And we're going to use power series. So we're going to first find a power series representation for this function. It's kind of our first step here. So let's get a power series representation for x over 1 plus x to the power 5. And when we have x terms in the numerator, kind of our common strategy is, let's break that x off. We can deal with that multiple later. So we can write this to really emphasize that. We can write this as x times 1 over 1 plus x to the power 5. And why do we do that? Well, we're always trying to think back to our Again, that one form that we're always referring back to. So let's write that down. What's our prototype? Well, that's 1 over 1 minus x, and we know that's the sum from n equals 0 to infinity of x to the power n. So we're always, when we see these fractions or when we see these functions, we're always trying to think, how can I get it to look like this? So this fraction here doesn't have an x in the numerator. Let's separate that off. That's kind of the motivation here. Let's get that x out of there. And then we see here we have this fraction 1 over 1 plus x to the 5. That's already looking better. All right. So we have the 1 here. The 1 in the denominator matches with the 1 in the denominator here. That's good. We have this addition sign. So we know what to do with that. We do a double negative. So we're going to write this as 1 over 1 minus negative x to the power 5. And what we're going to do is now we're going to treat this like a variable, this negative x to the power 5, and we're going to plug that into our kind of this standard form here, this prototype that we're always referring back to. So just plug negative x to the power 5 into here, and that's going to give us almost, well, it will, our power series representation for the function we're trying to integrate. So let's say we're converting here to our power series representation. So we're going to have x times, and now let's fill in our series, our power series. So it's going to be the sum from n equals 0 to infinity. And we're going to be plugging negative x to the power 5 in for x here. So we're going to have negative x to the power 5 raised to the n. Now we want to simplify this down. So let's break this negative 1 off. So we're going to have negative 1 raised to the power n, and then we'll have x to the power 5 raised to the power n. And once you get the hang of this, you can probably do some of these steps, without showing all of this. So we broke off that alternating piece. We have x raised to the 5th, all raised to the power n. We have multiple exponents here, so we can multiply those together. Again, we're doing the sum from n equals 0 to infinity. We have x to the power 5n. And the one thing we can do to really make this nice is this x, now we can multiply that in. So now we can bring that in. Once we have our power series representation for our main fraction part, this x is just kind of hanging off to the side here. We can bring that in, and when we do, we can multiply it into this x raised to the 5n and then add the exponents. So we're going to get the sum from n equals 0 to infinity of negative 1 raised to the power n times x raised to the 5n plus 1. All right, so there's our power series representation for this function here, x over 1 plus x to the power 5. So what we want to do now is we want to actually integrate this function. So we want to find the antiderivative of this function. So let's do that next. So we're going to actually do the integration. And let's think here. So we're going to do it two ways, just to really see how this process looks. We have our sigma notation here, but I think it's also helpful to see what the integration looks like if we write out the first few terms. So let's actually find the antiderivative. And we're going to do it a few ways just to see how it looks. So let's write our series we'll write it out. So it's the sum from n equals 0 to infinity of negative 1 raised to the power n times x raised to the 5n plus 1. But let's also write out the first few terms. So when n is 0, we're going to have x, positive x. Then when n is 1, we're going to have negative x to the power 6. So n equals 1, we're going to have 5 plus 1 here. And then when n is 2, we're going to have what? Plus x raised to the power 11. And then let's do one more. When n is 3, we're going to have minus x raised to the power 16. And then so on. So here's our power series representation for x over 1 plus x to the 5th, written out as either in sigma notation here or with just the first few terms written out. So let's actually see what the integration looks like. So let's integrate both sides. So we're going to integrate the sigma notation here. We're going to integrate the, let's just, I'm running out of room here. Let's do the, let's say it like this. So we're going to do the integration. So we're just going to integrate term by term. So if we look at our sigma notation here, x is our variable. X is the thing that we're integrating. So n is, it's really, it's our index number, but it's a constant. Really, x is our variable here. So when we look at this general term, negative 1 raised to the power n, that negative 1 raised to the power n is just a constant. So it's going to stay the same. And then we're going to do power rule for this power function, x to the 5n plus 1. I'm just going to do power rule. So what do? Keep x the same, add 1 to the exponent, so it's going to take us up to 5n plus 2. So we were at 5n plus 1. If we add 1, we get 5n plus 2. We take that new exponent, flip it, put it in front of the x. So we end up with 1 over 5n plus 2 in front. So that's what it looks like when we integrate the kind of the sigma notation here. What about if we integrate with it written out? What are we going to do? Well, we're just going to go through and integrate each of these terms individually. So what's the antiderivative of x? Well, it's 1/2 x squared. What's the antiderivative of negative x to the power 6? Well, it's negative x to the power 7 with 1 over 7 in front. What's the antiderivative of x to the power 11? Well, that's x to the power 12 with 1 over 12 in front. So we end up with 1 over 12x to the power 12. And let's do the last one here. What do we get when we integrate x to the power 16? Just power rule. So we get minus 1 over 17 times x to the 17, and that would keep going. So we're going to put this all together next, but right now we just found the power series representation for the function we're actually interested in integrating. And then we actually went through and found the antiderivative, did the integration. All right, so let's put this all together. So this is equal to the integral from 0 to 1/2. Let's write in what our power series representation was for the function. And what was it? Negative 1 to the n. Here we go. X to the 5n plus 1. we did the integration. So we found the antiderivative. Let's write out what that was again. So we found so this is really the same process as what we would normally do for a definite integral, except we have to find the power series representation first. But once we have that power series representation, well, then you just find the antiderivative like you normally would. So we found it to be -1 raised to the power n, x raised to the 5n times 1 over 5n plus 2 times x raised to the 5n plus 2. And I didn't include the plus c before because we're doing a definite integral. So we know normally with definite integrals we don't need to include the plus c. So here's our power series. And we're going to evaluate from x equals 0 to x equal 1/2. And then we evaluate just like we would. We're going to plug x equals 1/2 into this. We'll plug x equals 0 in and do the subtraction. So we're going to have the sum. What do we get when we plug 1/2 in? We're going to have the sum from n equals 0 to infinity of -1 raised to the power n over 5n plus 2 times 1/2 raised to the 5n plus 2. So I just plugged 1/2 in for x. Again, it's helpful to keep track. X is our variable. So I know there's n's here. N is just our constant, it's our index number here. So we're thinking of that as a constant. X right now is our variable. So this is what we get when we plug in the top number. And then we do the same thing. We plug in our lower number, x equals 0. And there we go. We've evaluated it. Now it turns out this is going to simplify nicely. And to see that, this is going to end up being just 0. Again, that's not always the case. So it just happened that the two series we looked at, when we plugged in x equals 0, it ended up being 0. But that's not always the case. So to really see why this simplifies to just 0, it's helpful to go back to what we got when we wrote out the first few terms. So sometimes that first term might be a constant, so you do want to check this. But when we had our original power series, we integrated it term by term. That gave us the first few terms of our power series for our antiderivative, and we see that these are all just powers of x, and there is no constant term there at the beginning. They all have an x in it. So when we plug 0 in, all of these powers of x are just going to be 0. So this whole second piece here ends up just simplifying to 0. So it turns out then that the value of this integral, we can think of it as a series. It's the sum from n equals 0 to infinity, -1 raised to the power n over 5n plus 2 times 1/2 raised to the 5n plus 2. So we can think of the value of this integral as a series. So this example really shows a few things. It shows how we can use power series to calculate a definite integral. And then we also saw kind of how the integration process works on a more specific scale, where we wrote out the first few terms, and then when we integrate, we just integrate each of those terms individually. We go term by term and do the integration. So same idea as what we saw for derivatives. We would just go term by term. All right, so that's going to do it. Now in the next lesson, what we're going to see is when we do these power series representations, we're always going back to this prototype, this kind of specific example that we're always referencing? Well, it turns out that a lot of functions have a power series representation. And there's kind of a more general way to figure it out. And we're going to see that next time. We're going to see how to find, given a general function, given a function, how can we find a power series representation for it without necessarily having to use this really kind of specific example here. This is a specific case of 1 over 1 minus x. How can we kind of expand that to consider potentially more functions? And that's what we're going to see next time. All right, so we'll see you then. Bye-bye.